let me explain the quiz question. We have a system, a discrete time system, whose input is x of n and output is y of n. And just like the differential equation form of continuous time systems, now I'm giving you a discrete time difference equation. And as a matter of fact, in the first examination, I remember that I have asked you a question like this. And I asked you the impulse response, if you remember. But then we didn't know the system to do that. We are somehow getting to the tools to determine the impulse response. But before the impulse response, you need to find the spectral response, which is the Fourier transform of impulse response from here. Can you find it? And let me give you a hint. Of course, you need to take the Fourier transform of this difference equation. And from there, let's see whether you can come up with h of e to the j omega, which is the system transfer function in frequency domain. Of course, even if you may not do it, even if you're not able to do it, you have to submit your quiz for attendance. So I'll give you like 2 minutes. Let's try to work on it. Okay, let me ask you this. How many of you guys are able to attack this problem or solve or have any kind of solution? A few of you. That's not a difficult thing, okay? It's a question that we expect you to be able to solve. So if you're not able to solve, or if you're not able to come up with a solution, then you must worry about that. Okay? Let's do it. Okay. As I say, your quizzes will not be evaluated anyway. They are just for attendance purposes. Without wasting any further time, let's attack this problem. We are asking the frequency response of a system with this kind of a difference equation. Now, the way to do it is to write everything in the Fourier domain. That is, take the Fourier transform of both sides of the equation. And here we have y e to the j omega, which is the Fourier transform of y of n, minus a times. What is the Fourier transform of yn minus 1? E to the minus j omega times y of e to the j omega is equal to x of e to the j omega. and in a parenthesis of y of e to the j omega, that makes 1 minus a times e to the minus j omega is equal to x of e to the j omega. And it is y over x in the Fourier domain that makes the frequency response. And this is equal to h of e to the j omega, by the way, is equal to y over x is 1 over this thing. 1 over 1 minus a e to the minus j omega. Isn't it? And so that's it. This is the answer. This is h of e to the j omega. But again, just like the things that we did for continuous Fourier transform, continuous time Fourier transform, there we had differential equations. Now we have difference equations, and it is now possible to proceed to the impulse response of this thing now. And how are we going to do that? By taking the inverse Fourier transform of this. So h of n is therefore the inverse Fourier transform of this expression. And this is one of the most simplest Fourier transforms that we already have. We already know the answer to this, in other words. It was the very first example that we saw. And it was a to the minus n. No, it's a to the n, u of n. So this is the impulse response then, which is the inverse Fourier transform. Or we know that if you take the Fourier transform of this expression, which was the first example, as I have to repeat, it was this. So the inverse Fourier transform is therefore a to the n u of n. Now you must ask yourselves this question. If I give you a longer difference equation, how shall you attack the problem? You have to do the same thing. You have to just come up with an expression, and it's most probably something like 1 over 1 minus a e to the j omega minus b e to the minus j2 omega, for instance. Something like that. Over there, the easiest way of attacking this problem is to assume that e to the j omega is equal to an entity. So you may come up with something like this. 1 minus a e to the minus j omega, which is a first delay coming from y of n minus 1. If there is a y of n minus 2, for example, minus b times y of n minus 2, and a further expression, that would appear here as minus b e to the minus j 2 omega. And if there is like other terms of x of n minus 1, x of n minus 2, then it will be in the numerator. But numerators are easy because they will only correspond to delays. There will be an e to the minus j omega, for example, in the numerator. What does it mean? You find the inverse Fourier transform, you find this, and then you apply a delay to the overall thing. What is one delayed version of the top one, for example? It is a to the n minus 1 u of n minus 1. Delay by 1, for example. Simple. So the numerator is easy part. The denominator, however, if it is a second order system like this, it becomes in a quadratic form. But can you see the quadratic form here? In order to see the quadratic form, the best way to attack the problem is to say that e to the minus j omega, or e to the j omega, in fact, is make this substitution. E to the j omega is equal to, let's call it z. It's just a name. Then this will be 1 over 1 minus a times z to the minus 1, or 1 over z, z inverse, minus b z to the minus 2. Now, as you see, in the denominator, it's in the quadratic form. And you have to find the roots and make it two first order solutions. A summation of a first order plus a summation of another first order. You can split into two forms. And every first order system will make this. It will be something like this. The other will be a different form of one-sided exponential like that. So you will have two exponential forms. One of them this, one of them the other. So that will be the solution. That's how you solve it. Okay? You have to attack the problem like that. If I ask a third order difference equation, y of n minus 1, y of n minus 2, and y of n minus 3, then that question will be a torture. Because it is meaningless. I mean, you understand the point. You know how to attack the problem. So if I give you more and more complicated questions, it's pointless. It doesn't contribute to the idea of solving the questions in this way. However, you can be asked a question in an indirect way as well. Like this, for example. I may give you this as h of n, and I may ask you, what is the difference equation? Okay, that may be easily a question. Now, how do you find the difference equation? Whose impulse response is this? Now, you need to find the Fourier transform of this first. What is h of e to the j omega? And you will find this. And you will insert that expression here and say that it is equal to y of e to the j omega over x of e to the j omega. Then make a cross multiplication and come up with this equation. Expand that equation and make it like this. And take the inverse Fourier transform, and you come up with the difference equation. That is also possible, which is completely the inverse path. Yeah, and you should be able to do that as well. So I may start from anywhere of these three things. What are they? The difference equation, the frequency response, and the impulse response. These three things equally identify a system. And I may give you this and ask this. I may give you this and ask this. I may give you this and ask this or this. Whichever. They are convertible to one another. All right? Of course, in an exam question, it will not be overly complicated. It cannot be it doesn't make sense if I ask a question of third order or anything, but second order, up to second order I may ask, okay? You may expect questions like that in the examination. That's what I can say regarding the system responses. Okay, so that was sort of a property, and we started it as a quiz question. Now, another property. Let's continue with the properties and let's finish all these properties of the discrete time Fourier transform. By the way, soon we will come up with more reasonable ways to attack the spectrum problem of Fourier transforms and things like that. For example, I said that e to the j omega is equal to z. And I make this name substitution for a reason. There is a reason to that. Because it is indeed denoted as z in another transform expression, which is not in terms of the frequency parameter, which is omega, but it is in terms of this new thing, z. And it is called, as the name implies, the z transform. We haven't seen the z transform yet, but you already understand what it is all about. This is the Fourier transform, h of e to the j omega, and this is the z transform, which is h of z, as simple as that. And the relation between them is this. And usually the students are more comfortable with this one, because it's smaller, more compact way of expressing discrete time systems. Anyway, we will come back to that through the ends of this course. Let's continue with the final remarks of these properties. And the new one is the multiplication property. Because convolution we already know. we didn't even mention about that, but it's so obvious. If you convolve x of n and h of n to obtain y of n, that means x of e to the j omega times h of e to the j omega is equal to y of e to the j omega. And in fact, this is why, so the convolution in time will correspond to multiplication in frequency. And that's in fact why we have h of e to the j omega equals y e to the j omega over x e to the j omega. That's why, that's how we solve that problem anyway. But this is an expected property, and it also exists in continuous time as well. The more, a little bit different property is in terms of multiplication in time. Do you remember what we were, how we were denoting multiplication in time for continuous time signals? For example, what was the terminology when I say I'm multiplying x of t with cosine omega 0 t? When I multiply with a cosine, there was a name for that. Do you remember that? Modulation, yeah. So this multiplication thing is a modulation. And do you remember how the frequency was affected with that? So the multiplication is in time is this. Y of n is equal to, let's call x1 of n times x2 of n. So my new signal is in terms of the multiplication of the two. Then what is y of e to the j omega? The Fourier transform of this multiplication output in terms of the Fourier transform of this and the Fourier transform of this. It must be a convolution. And it is indeed a convolution, but it's a little bit different. There's a 1 over 2 pi, as we already have in continuous time as well, so that's not a big problem. This integral, I'm not indicating the limits yet, but the limits are important. x1 e to the, now that's a problem in convolution, right? How do we write convolution in time? For example, x1 of t convolution x2 of t. What is that? Integral x1 of tau x2 of t minus tau d tau. So x1 of tau, but it was omega, so it's not t versus tau. Now we have to apply another notation. It is omega versus, the book uses theta, so that's what I will use. Theta will be my new tau argument. So x1 of e to the j tau, and it is overly complicated. You see, it's not x1 of tau or x1 of theta. It is x1 of e to the j theta. And x2 of t minus tau, e to the j omega minus theta d theta. So this is the convolution, but it looks unfamiliar. But it is. Theta is tau, omega minus theta is t minus tau, d tau is d theta. So this is the convolution, but the convolution is now in a duration of 2 pi. And that is the critical thing. Theta is from 0 to 2 pi, for example, or it is from minus pi to pi. Any duration, any starting point, plus 2 pi of that. And that 2 pi integration is indicated with a different name. The name of this one is not convolution anymore. It is called circular convolution. And the reason it is called a circular convolution is that both x1 and x2 are circular signals. In fact, they are periodic. That's why they are circular. After one period, you come to the same point, one circle. If you linearly convolve two periodic signals, you get infinity. In other words, if this is from minus infinity to infinity, this integration will give you infinity because both x1 of e to the j omega and x2 of e to the j omega. Both of these signals are infinite extent. They are periodic. So when you convolve them, you come up with a huge sequence from minus infinity to infinity. And if you accumulate all those multiplications, you will get infinity. In order not to get infinity, you have to take only a 2 pi period or 2 pi portion of the overall expression. And it's therefore a little bit difficult. You have to be careful. For example, in the book there is an example. I will repeat the question here, but I urge you to look at the book to see how the convolution will look like. The first one, x1 of e to the j omega, is like this. So this is x1 of e to the j omega. It is from minus pi over 2 to pi over 2, basically. In the center it is this, and then it is 2 pi periodically replicated everywhere. All right? So this is your first signal, and you need to circularly convolve it with another low-pass filter, but that new low-pass filter is slightly different. It's not up to pi over 2. This is pi over 2, this is pi again. It is in the middle between pi over 2 and pi, which is 3 pi over 4. And up to minus 3 pi over 4. So this is the fundamental module in the center, and you have to make this thing 2 pi periodic. And it becomes 2 pi periodic like this. As you see, this new low-pass filter's passband is wider than the passband of the top one. And so the separation, which is 0, the stop band, is a little bit narrower around pi. That's the difference. Now, if you try to just convolve these two things, and how do you do that? You flip around one of them and slide and take a look at the overlapping portions. Now, you see, when you flip around this one, for example, the second one, well, you get the same thing anyway. It's symmetric completely. And then slide. For example, at this kind of a situation where the amount of shift is 0, some portions from these two will overlap. It will be an overlap of this amount, in fact, and then you have to take the integral. Suppose that you slide it towards left, let's assume. After some time, some portions will not be overlapping with the top one, but if you go further towards left, this portion, this low-pass segment, will start to overlap with the other one as well. It will be a little bit overlapping with this and partially overlapping with this. So the overlapping is a bit complicated, okay? You have to be careful. Just try to draw it and see how the convolution result looks like after sliding. And the amount of slide you have to apply is limited to 2 pi. Shift towards the left by an amount of pi and towards the right by an amount of pi. So between minus pi and pi, it will be a 2 pi shift. And the integral must be after overlapping. The integration must be taken within this limit only, from minus pi to pi, for example. Because if you take the integral from minus infinity to infinity, this will overlap with this one, this will overlap with this one, this will overlap with this one, everything will overlap, and when you integrate all those overlapping regions, you will get an infinity. So you have to start and end at a length of 2 pi. It could also be from 0 to 2 pi as well, but for this question I think it's easier to evaluate the overlapping from minus pi to pi. Just do it, okay? You need to do it. And this is the example in the book anyway. So it's in the book, the answer is there. But make sure that you understand and you are able to reproduce such a circular convolution. And interestingly, the convolution in frequency is continuous. Although the signal y of n and x of n are discrete signals, their Fourier transforms are continuous, omega. So this convolution is a continuous convolution, but it is circular because the integration limits are with the duration of 2 pi only. Now we are approaching the final properties, final remarks. Duality is one of them, but it's a little bit difficult to explain because the duality is not for the Fourier transform. It's not for the discrete time Fourier transform. It is for the discrete time Fourier series. Do you remember what the Fourier transform of a continuous, the Fourier transform of a discrete time periodic signal? If the signal is periodic, you have Fourier series coefficients, not the Fourier transform. And you insert impulses to the positions of the Fourier series coefficients. That's how we were attacking the problem. It may be best to start with an example without trying to explain any further. Suppose that you have x of n, which is periodic, but I'm indicating only one period of that, like this. 1/9 sine 5 pi n over 9 over sine pi n over 9 when n is not an integer times 9, and it is equal to 5/9 when n is equal to an integer times 9. For example, when n is equal to 0. L is, this is L, any integer L times 9 and any integer L times 9 here. When it is not equal to an integer times 9, then it is expressed like this. When it is equal to an integer times 9, it is expressed like this. The easiest way to understand this problem is this, in the central portions except the DC, which is n is equal to 0, it is like this. When n is equal to 0, which 0 times 9 in other words, it is equal to 5/9. So this is the, it is like the DC, and the others are like this, and it is periodically replicating. So the period here is 9. As you see, it is deliberately fabricated question. It's quite difficult to fabricate examples of duality, and it already looks like the Fourier series coefficients of something. Okay, that's what you have to be looking at. If you take a look at the typical Fourier pairs, you will notice this. It's there. This is the Fourier. These are the Fourier series coefficients of what? This is the discrete time sink. So it's like the sink. And what is sink? The Fourier transform of? No? Rectangular. So immediately you expect that if the rectangular thing periodic will have the Fourier series coefficients like this somehow, then the Fourier series coefficients of this thing must be like this. That is the duality. And to be more precise, by the way, I'm drawing something quite accurate unintentionally. This 5/9 is indicating that 5 of the samples are non-zero, there are 1, and the period is 9, so there are 4 more 0 values, and 5 ones and 4 more zeros, etc. So this is the signal which exactly produces these Fourier series coefficients. And I'm going to call this signal G of n. G of n is this. And here it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. -1, -2. And it goes on like this. So as you see, the period is 9 because this central 1 point is repeating itself at here. Exactly. So the period is 9, and the way to express G of n systematically would be like this. It's equal to 1 when n is less than or equal to 2, and 0 when it is greater than 2 in magnitude and less than or equal to 4. And then repeat at a period of 9. That's how you can express this G of n. Since G of n has the Fourier series coefficients like this, so the Fourier series coefficients of G of n are equal to x of n, the Fourier series coefficients of G of n are equal to x of n, then the Fourier series coefficients of x of n will be equal to what? They will be equal to G of n. But first of all, they must be inverted in order, and then they must be scaled by 1 over capital N, which is the period, times x of G of minus k. Let me call these ones x of k's, okay? Because usually we are using k as the index of Fourier series coefficients. So the Fourier series coefficients of G of n are equal to xk. Well, previously we were calling that one as ak. You remember that? The Fourier series coefficients, ak's. So ak's are xk's. Then the Fourier series coefficients of xn are 1 over n of g minus k's. They are inverted in order. If everything works perfectly like this, because these are perfectly symmetric, G of n is symmetric around the origin, and x of n is also symmetric around origin, by the way. So G of x of minus n is equal to x of n, in other words. Then you will not notice this effect of minus k, but normally it's like this. And if you remember the optical example, if you take twice the Fourier transform, as I say, you obtain the negative of the image. The candle was forward upwards here. After passing through a lens, the candle becomes inverted. That is, G of n is Fourier transformed to x, and then x is further transformed to G of minus k. So the candle is not upward anymore, it is downwards at the other side. This property is known as duality, Unfortunately, there is no reasonable question that could be asked from this topic. Because, honestly speaking, this is the only reasonable example that you can come up with. Sink and rectangle. If you have other typical pairs, they could also be asked, but in discrete time, we don't have things like that, where this is periodic and this is also periodic. Fourier series are periodic by 9, the signal is periodic by 9, or vice versa, using this duality property. Therefore, I must show you this example as perhaps the only example. You may not expect a question which requires this, at least in discrete time. In continuous time, the duality property is more useful because everything is flexible. We are limited to periodic signals in discrete time, and periodic signals are very limited. In continuous time, we have everything. So I'll probably ask questions from continuous time duality property. This is a property that I may not ask any question. Okay. Well, as a matter of fact, that's about it. The Fourier series properties are like this in discrete time. And we haven't seen all the properties, by the way. All the properties are listed in the book. Some of these properties are easy to show, like the difference, because the difference was immediately obtained by taking the Fourier transform of both sides of the equation. Some of them may require more thinking, but for the final exam, I intend to ask at least one, but it may be more, show that question, which is a proof question. And those proof questions will be extracted from the properties. You will have a property table with you in the final. In all the exams, you have them anyway, some tables. But please work on why they are valid properties. Most of the proofs are already in the book, and I have mentioned about some of them as well. But for example, for some, I didn't mention about. For example, I didn't say why this is the case. I just told you that the duality is like this, it works like this. Did I prove it to you? Did I prove the validity of this one? No, I didn't. Some are easy, some are not. Please, for the final examination, work on the constructions of those properties as well, because I will probably ask one or two of them as show that questions, apart from other normal problem solving questions, because I believe that these the construction of these properties is also critical, and we don't have that much time to show and prove each and every property, so you have to work a little bit on those things. You will expect a question like that as well. So we are finished with Fourier transform. Tomorrow we will continue with a completely new topic. Nope, it's not Laplace, it will be sampling. That is continuous time to discrete time conversion. Quizlerinizi oraya bırakmayı unutmayın.